Check. Check. Okay, so let's go ahead and begin. So everybody knows that a week from tomorrow we have final exam in this course. Please bring your UCSC picture ID. To the exam, okay? So PA5 was extended again to Monday. That's last night. I'm sorry, that's 2 nights ago. So it was due to close it yesterday at 10 a.m. and then I told some people that I would, delay closing it. I waited until 7:30 or 8 p.m., somewhere in that range, to actually close it. So a few people were able to get it in under the wire, but it is now closed for submissions. I hope you got something turned in. I hope you took my advice on Wednesday and got something turned in by yesterday at the latest. And this is homework 8 that you're just now turning in, so there's nothing else to do except study for the final, okay? I will post some review problems shortly, like tonight or something like that, at least a week ahead of time. I'll eventually put out, maybe this weekend, I'll put out some selected solutions to those review problems, and that's a good thing to look at for the final. Should look at homeworks, including homework 8 solutions, which I'll get posted shortly. Is the final cumulative? Yes, it is. Final is cumulative. You do not need a Scantron. There will be no Scantron. Just kidding?
No, I'm kidding. I know we don't.
All right. Sometimes I wish I did use Scantron. It'd be much easier to grade the thing. We take almost, I don't know, I've reserved about 10 hours in a conference room to do the grading with like 17 people to do it. So it's a nightmare grading your papers. I hope you know that. Go ahead, ask your question.
Is most of the final going to be focusing on stuff after the second test?
I would say, first of all, everything that we've covered from day one until Friday, end of business, will be fair game for the final, but I'd say there's a slight emphasis on the material since the last midterm. That's not that much material, but a slight emphasis on that. So yeah, there'll probably be another master theorem problem. There will probably be, something to do with asymptotic growth rates. There will be, stuff that you could have seen on the first or second midterm, but there'll also be stuff. So this is a third midterm thrown in. Your question? That I don't know. I'm a little more worried about PA4 than PA5. Grader for PA5 is working on it now. I don't know how far along PA4 is to be graded. PA3 is graded, correct? You have your PA3 scores. Okay. Yeah, these take a long time to do, but my instructions to the graders is always better right than fast. Do it, try to do the best job you can, and that takes time. And it's even with the automation. We automate a great deal of this, but it still takes time. Go ahead. You mean like a review session next week? I have not planned any. By the way, don't show up at my office hours next week. I mean, that's out, right? Office hours end tomorrow. That's my last office hour. And there are no lab sessions next week. But if one of the TAs decides to turn their lab session into a review session, as they sometimes do, they'll post that on Piazza. Or if one of them decides, and I give them the option to do that, to hold an outside class, outside lab session review, that's devoted to just going over the review problems or something, then all of that would be posted on Piazza. Probably on the web page too, but on Piazza at the least. Anything else? Yeah, go ahead.
I didn't pick up my midterm too. Did I pick that up from the TA or you?
From me. Right, so that's where all old papers go, including homeworks, midterms. They're in my office. Come to my office hours and you can have them. You bet. Okay. Well, I've been complaining, and you've kind of had to endure my whining about this all quarter, the fact that we don't have the same amount of time, and we didn't really ever have enough time, in my opinion, to start with, but then they took away 5 minutes. So, we've kind of reached the end of the rope. We're really starting to suffer because of that, because we can't get as far as I think that we need to get and all the things that you need to know. I guess we just have to accept that and just, I've been pulling my hair out and saying, what do I do? What do I do? All I can do is the best I can do. We're just going to cover as much material as we can up until Friday, and I'm not going to try to go particularly fast anymore because it's not getting me anywhere. I'll only go a little bit faster than I ordinarily would, and I don't gain that much. I've got to just, what I really have to do is, now that they've redesigned our class schedules, I have to redesign this course. I have to throw out some large topics. I don't know exactly what I'll do. Maybe even change textbooks. I would hate to do that because I find this an excellent textbook, but I don't know what I'll do in the future. Go ahead. You could go back to past offerings. I'll tell you what I would do next. I would do, when we're done with single source shortest paths in a weighted graph, Bellman, Ford, and Dijkstra, which I think I'll be able to finish decently. I would talk about two more things. One is red-black trees, which is a strategy for taking a binary search tree and keeping it balanced. What does balanced mean? It means as close to the floor log base 2n height as you can get, right? Remember, a linear linked list is a binary tree, right? Every node has one child. Instead of the possible two, it only has one child. And you get just a linear linked list. Searching a linear linked list takes linear time, right? Its length is n minus 1 if it has n nodes. But an almost complete binary tree, that's the best binary tree because its height is floor log base 2 of n. So log n is the best runtime you can get searching such a structure, and theta n is the worst case you can get. So if the structure is closer to theta n than to, closer to theta log n than to theta n, closer to log than linear height, we call that a balanced tree. And red-black trees is a strategy for building a binary search tree and then making sure that when you do insertions and deletes, you keep it balanced. You keep it close to the minimum possible height so that future searches are going to be efficient and future insertions and deletions will be efficient. It's a wonderful and beautiful strategy. I used to cover it in great detail. I don't see how I can do it justice now. So that's chapters, I believe, 13 and 14 in the textbook. So if you want to cover it on your own, read those sections. Maybe it's 12 and 13, but I think it's 13 and 14. Another topic that I would cover, I might be able to touch on, is another pure graph theory topic, and that's the notion of a minimum weight spanning tree in a graph. There's two famous algorithms, Kruskall's algorithm and Prim's algorithm, that you start with a weighted undirected graph, and amongst all the spanning trees, what's a spanning tree in a graph? That's a subgraph of the graph that is a tree and includes all vertices. So spanning means it touches all vertices, and it's a tree. Okay, so it necessarily has n minus 1 edges. It's a minimally connected subset of the edge set, right? The smallest number of edges you can have in your connected graph and stay connected. All right, the idea is to reduce as far as possible the total weight of such a tree. You have weights on the edges. So the weight of the tree is the sum of the weights of all the edges. So there's a problem. Find a minimum weight spanning tree in a graph. If you think of your graph as some kind of communications networks and the weights as the cost of maintaining reliability of some connection between two nodes in the network, then that's a practical thing to want to know how to do. Find a minimal set of edges that you could reinforce and always maintain connectivity. That's the kind of thing you should look at. Or that's the kind of application you should have in the back of your mind. So Kruskal and Prim, one of them uses priority queue and is most efficient with a heap implemented priority queue. All right, so that's one other topic. And that's covered in chapter 25, I think. But all this stuff is in the textbook. All right. Was there one other question you had? Go ahead. Unfortunately, I think they throw them away. I don't do the webcasts. They are captured automatically, and I believe I don't think they're archived, but they are?
Yeah, I got to it one time, but it's like a weird way to get to it.
Oh, okay.
It's like not normal.
It's not normal. Who did you contact in order to figure out how to do that?
Professor Google.
Oh, okay. So a famous tenure-track faculty member. Go ahead.
Yeah, there's, I don't know, I can show you after class if you want, and there's no way to get to them, but it's not normal at all.
I see. I wouldn't do that. I would probably try to talk to the people at Webcast. So I would send some kind of a help message to ITS or Webcast and say, do you have archives of these past lectures? And I've only been webcasting my lectures for maybe 3 years now anyway, so you wouldn't be able to go beyond that. When I look at what I was doing 10 years ago, I can't believe how much I did, and I don't know how I did it. I did it all on a blackboard. So in a small class with maybe 50 students in it. All right, that's enough of that. Where were we last time? We're talking about the infrastructure for two graph algorithms that we want to study. The algorithms are Dijkstra's algorithm and the Bellman-Ford algorithm. Both of them solve the single source shortest paths problem in a weighted graph. Both a directed and an undirected graph, but for simplicity, we just assume throughout the discussion that these are directed graphs with weights on the edges. There's the initialization sub-algorithm. Right, just initializes everything with respect to a given source. Source has distance estimate 0. Everything else has distance estimate infinity. Parent nil. and then the relax operation. And the intuition behind relax is that if you already know, if you already know a path from source to x, you can see if your current known path to y is improvable by first going through x. The precondition, of course, is that there is an edge from x to y. So here's the picture for it. Notice it even works if you don't know a path to y. You just know some path to x. So dx is finite, but if you don't know a path to y, then dy is infinite currently. And that infinity is much worse than this finite number plus that finite number. So this is how you first find a path to y, by discovering it as some neighbor of x. So you see what I'm saying? These algorithms, Dijkstra and Bellman-Ford, in principle, they could discover a vertex multiple times as they find better and better paths. So in order to prove the usefulness of these two subalgorithms, especially relax, we consider what happens in sequences of calls to relax. So to start with, we consider arbitrary relax that edge, relax that edge, relax that edge, relax that edge, any sequence at all. When we get to the particular algorithms, the important thing and the strategy of both those algorithms is the order in which they choose to relax edges. Okay, lemma 1 said, let x be in V. Suppose after initializing with respect to the source, some sequence, notice I'm not specific about the sequence at all, some sequence, some arbitrary sequence of calls to relax results in dx being finite. Then G must contain an Sx path of weight that finite number. Okay? In other words, every time D is assigned a finite number, you're finding a path. A D value for a vertex is assigned a finite number. You're discovering a path, and sometimes a new path. If it's ever lowered, you're discovering a new path from source to that vertex. Okay, that was a homework problem. How many people think they made some serious progress on that? I think it's a basic theorem. It's not the strategy that the book uses, by the way, for proving correctness of either of these two algorithms, but I find it much more direct than what they do. So a lot of people thought they made progress. I'm going to prove it today, even though you're going to see the solutions. The reason I'm going to bother to prove it in class is because I do sometimes put that on final exams. And it's a nice example of an induction proof and why we have this technique and why we're so obsessed with knowing how to prove things by induction. This is a typical example of something that really is lemma 1, that is most efficiently proved by induction. Okay, lemma 2, I did prove this. It uses lemma 1 in its proof. After initialize, the inequality true distance from S to X is always less than or equal to the distance estimate from S to X. And that's going to be true, and that will be maintained no matter what order and what sequence of calls to relax. Notice it's always true to begin with, because initially dx is infinite. And if delta Sx can be defined at all, delta Ss can be defined at all, it's 0, and ds is initialized to be 0. So this is certainly true for a sequence consisting of no relaxations, right? A sequence of length 0. This is not done by induction, because we already did the induction proof in proving lemma 1. Here's the proof. It's a proof by contradiction. Suppose that this inequality is violated for some vertex x and some sequence of calls to relax. All right, so there exists a sequence of calls to relax that causes this inequality, the negation of that inequality. We are looking at the same thing, aren't we? Good. The negation, so this inequality to be true at some point. Well, then necessarily dx is finite, because the biggest that can be is infinity, right? So, but this is a strict inequality. So, by lemma 1, G must contain an Sx path of weight dx, but dx is strictly less than the minimum of any possible Sx path. That is a violation of the very definition of delta Sx. See how simple that argument is? I'd like to put that on exams. I consider that an easy problem. You just have to remember the words. You have to remember how to say it sensibly, right? Okay, so this contradiction shows that you can't have such a sequence of relaxations. So that's a fact about all relaxation sequences. All right, so there's one more lemma along these lines, lemma 3. Let me state lemma 3, and I'll come back and prove lemma 1, and then we'll go on to Bellman-Ford. Lemma 3 has a fancy name. It's called the path relaxation property. If P, starting at S, so P is a path, I'll call S x naught for these purposes, x1 up to xk, is a minimum weight S to xk path, and now here's a specific relaxation sequence, and the edges of P are relaxed in order. Relaxed ED, right? I'm taking an algorithm and turning it into a verb. Relaxed in order. The order in which they appear along the path, right? So x naught, x1 is relaxed, then x1, x2 is relaxed, then xk minus 1, xk is relaxed. So you just relax the edges along the order, along the edge, along the path in the order that they appear on the path. Then dxk at that time, after all those relaxations, will be equal to delta Sxk. So the distance estimate, dxk, will have converged. It might have, it started at infinity, it might have dropped down to some finite values as you found better and better paths, but eventually it will have reached its minimum possible value. So that's true, and more is true. Let me, there we go. Also, or moreover, up? How about I just do this? I see, I need to pull out. How's that? Is that good? Maybe I should pull this one out. There, that looks good. Come on. There we go. Moreover, this remains true if these edge relaxations are interspersed with any number of arbitrary relaxations. This is true. Regardless of any other relaxation steps that may occur. Even if they're interspersed with the above relaxations. Even if interspersed. In other words, if you have any relaxation sequence that has this as a subsequence, then that relaxation sequence must cause this endpoint d value to have converged. That's the path relaxation property. The proof is, I'm not going to do it, is by induction on K. K is the number of edges in P. Induction on that number. And you can see that if K equals 0, then we're back to a base case where there's no relaxations. Well, you have any relaxation sequence at all has the empty sequence as a subsequence, and indeed, since your endpoint is S itself, because K is 0, ds has converged. It converged as soon as you did initialize. Initialize sets it to the right value. So that would be the base case of your induction. See the book 24, section 2415, page 673. All right, I won't go any further than that. When I show you Bellman-Ford, you'll see that this, the correctness of Bellman-Ford will be obvious from just this theorem. All right, so let's go back to lemma 1. I told you I would prove lemma 1. Okay. Even though it's a homework problem, let X be in vertex set, and suppose initialize G with respect to S is executed. Suppose some sequence of calls to relax a relaxation sequence occurs, right? Some sequence of calls to relax results in dx being finite. Then G contains an Sx path. of length, sorry, of weight that finite number. Okay, so let's prove this. The proof is by induction on the number of calls to relax. Let n equal number of calls to relax. I don't know anything about this relaxation sequence other than the number of calls to relax there was in it. So base case, if n equals 0, then the only finite d value is that of the source, is S, i.e. must have x equals S. Right? That's the only way the hypothesis can be true, is if x equals S. Indeed, there is an SS path of length 0. Of weight, I should say, of weight ds, which is 0 after no relaxations, just an initialize, namely the trivial path. That's the base case. So the theorem is true if the number of relaxations in the sequence is 0. It's a strong induction. Strong induction form 2D. Okay. So let let n number of relaxations be strictly greater than 0. What do I have to do here? Have to explicitly state the induction hypothesis and I have to explicitly state the proposition to be proved on the induction step. And then I have to prove the induction, that proposition. And I have to say at what point I am using the induction hypothesis. That's what you have to do to get full credit. So I'm going to try to illustrate that. Assume, I'm going to use a different letter than X, because I want to use the letter X in that proposition to be proved on the induction step. You know, the induction conclusion. That's the letter I want to use then. So I want to state the induction hypothesis using a different letter to avoid confusion. Assume for any vertex u that if du becomes finite, after how many? Less than n, fewer than n relaxations, then, what's the conclusion of this theorem? Then G contains an SU path of weight, that finite value, du. Okay, that is my explicit statement of the induction hypothesis. Assume the theorem is true for relaxation sequences whose length is strictly less than n. I'm assuming that all dominoes up to but not including the nth domino have fallen in the domino analogy. All right, so what must we show? We must show that if X is a vertex and dx becomes finite after n relaxations, then what's the conclusion? G contains an SX path. Of weight, that finite value, dx. Okay? All right, so how are we going to show this? This is an if-then statement. So I better assume the hypothesis and try to draw the conclusion. Try to prove the conclusion. All right, so suppose let X be in V, and suppose some relaxation sequence causes dx to be finite. Okay. I've got to somehow construct an SX path of weight dx. And I've got to use the induction hypothesis along the way. All right, well, what can I say? All right, so for dx to have become finite, some edge with x as terminus must have been relaxed in the sequence, because it's only the terminus that gets changed, that gets its d value changed in relaxation, right? It's only the vertex that you're going to that is altered. So then some edge of the form terminus x must have been relaxed. In the sequence. And let's give a name to the vertex that comes before x, or the origin of that edge. So, well, I want to use yet another letter. Let's call it y. Haven't used y yet. Let y be the origin of that edge. Okay? So, on that call, to relax yx. Unfortunately, I have the order swapped than when I originally wrote the relax code, okay? Well, we can live with that. On that call to relax yx, dx was set to, oh, by the way, don't be fooled. I'm not saying that this relaxation of this edge that caused dx to be finite was the last relaxation step in the sequence, but somewhere in that sequence was a call to relax an edge that ends in x. So we're not necessarily talking about the last relaxation in that sequence. But on that call to relax yx, dx was set to dy plus the weight of the edge yx. Right? Dx was compared to this number, found to be bigger, and so therefore replaced with this smaller number. That's how relax works. Now, since we suppose that this number, dx, is finite, it must have been that dy was finite before this call to relax. Since we suppose this number to be finite, dy must have been finite before this call to relax. Okay. Well, in other words, dy became finite after a sequence of fewer than n relaxations. Because I don't know where in the relaxation sequence this relaxation occurs, but the furthest it could be would be, the last it could be was the nth. And the closest, right, so, since dy became finite in some earlier one, it had to have been in fewer than n relaxations. Does that make sense? Okay, so therefore, dy became finite after fewer than n relaxations. Okay. Wow. dy became finite after fewer than n relaxations. Too bad I don't have a hypothesis sitting around that I could use to conclude something about the vertex y. That nobody's laughing, everybody's staring at me like, what's this guy, what is he talking about? Right? You know what to do now, right? It's what hypothesis should I use? The induction hypothesis says precisely, where was it? Back a couple of pages, says precisely that for any u, right? I used a neutral letter here. Now I want to apply it to the vertex y. For any u, if du becomes finite after fewer than n relaxations, then G contains an SU path of weight du. So, by the induction hypothesis, G contains an SY path of length, or of weight, dy, that finite number. Just to help us, let's draw a picture of it. Here's S, here's some path that ends with y. Its weight is dy, and here's x, and here's the edge y to x, and its weight is wyx. All right, so remember what we need to do. Remember what we're trying to do. We're trying to show that there exists an Sx path of weight dx. Now, is there an SX path staring us in the face, slapping us in the face? Right? Have I drawn an SX path? Yeah, follow this path that the induction hypothesis gives us from S to Y, and then continue along the edge from Y to X, whose weight is WYX. That is an SX path. And what's its weight? It's this weight plus that weight. And what's that equal to? dx. And that's what we were looking for. Okay. I'm getting too excited. Better take my heart medicine or something. I'm just kidding. My heart is fine. My heart is fine. That path followed by the edge y to x constitutes an SX path of weight dx, but what's dx? dy, as I just said, plus weight of yx, which is what we were looking for as required. Let's just end the proof that way. The SX path that we're looking for exists. Okay, the whole thing is kind of trivial. Every single step is a sort of a triviality, but it adds up to an important theorem. And I like this proof because it's a good example of how to think your way through an induction proof that has nothing to do with the summation formula or anything like that. Go ahead. Well, the word hypothesis simply means what you assume to be true. Yeah, that's what hypothesis, the word hypothesis means. That which is assumed true. Okay, well, enough of the infrastructure. We have these three lemmas. As I said, these algorithms are pretty easy to understand once you understand those three lemmas and how they work and how they work together. Let's look at Bellman-Ford. So this is page 7. First of all, a call to initialize. All the relaxation sequences that lemmas 1, 2, and 3 refer to begin with initialization. And then, for I equals 1 to v minus 1, length of v, or n minus 1, or n, I didn't put n here. The thing to not be fooled by is n in this proof doesn't stand for the number of vertices. It stands for the number of relaxations. So that's kind of an oddball usage of the letter n. I'm not using n here. I'm using size of v, number of vertices minus 1. So in this for loop, I'm just doing something n minus 1, or number of vertices minus 1 times. What do I do? For each edge in the edge set, relax it. So if you look at this loop 2, 3, 4, it's kind of crazy because it just says relax all edges, and it doesn't even specify in what order to relax the edges. It just says relax all edges. You pick the order. Relax all edges, then relax all edges, and then relax all edges, and then relax all edges, and you keep repeating that n minus 1 times, or rather v minus 1 times. Let's just pause right here right before we even look at line 5. Just pause right there. And and suppose that single source shortest paths is solvable in G with respect to the source S. In other words, single source, this graph does not have a negative weight cycle reachable from the source. Remember, Bellman-Ford allows negative weight edges, so we have to consider that possibility. Are there negative weight cycles reachable from the source? If there are, then SSSP has no solution, or it's not solved by this, let's put it that way. But if, if no such negative weight cycle is reachable from the source, then there is no problem. Now consider the path relaxation property, lemma 3. That implies now that all the d values have converged. All the d values have converged. Why? Because, look, the maximum length of a path is v minus 1, is it not? Every path is a tree, has no cycles. And the maximum number of vertices in a path is the number of vertices in the graph, which is v. So the number of edges along the biggest path, the path with the most vertices in it, would be v minus 1. So every shortest path lies at the end, every vertex lies at that's reachable from S, lies at the end of a shortest path with at most v minus 1 edges in it. Did that make sense? Every shortest path lies at the end, say it again, every vertex that's reachable from S lies at the end of a shortest path that has at most n minus 1 or v minus 1 edges in it. Okay, so therefore, on the first pass over the edge set, I have relaxed all first edges along all shortest paths. And on the second pass over the edge set, I have relaxed all second edges along all shortest paths. And on the third pass over the edge set, I have relaxed all third edges along all shortest paths. All right? So there's an extravagant over-relaxation going on here, right? We're extravagantly relaxing a bunch of things we don't need to, but the important thing is to not leave anything out. So every shortest path has this is a subsequence of this relaxation sequence. Okay, remember the path relaxation property. If you have a shortest path and you relax the edges in that order, the endpoint has converged. And it doesn't matter what other relaxations are interspersed. So every shortest path is a subsequence that you want to hit, right? But every such shortest path gives rise to a subsequence of this relaxation sequence. Did that make sense? I don't think I'm saying it right because everybody's staring at me like I'm crazy. Was there a question out here? Go ahead.
So the only way for that, like the first two formulas actually be uniform away is in like equivalently for the path to actually be uniform because a straight path with one vertice connecting to one before.
Say that one more time.
Is the only way for like the path to actually be a shortest path of v minus 1 is like if there's a straight graph, a straight path with this vertice.
The graph itself could be a path. I mean, yeah, it could be one path.
So that's the only way that those formulas will be executed to like their
I mean, here let's draw a picture of a graph with how about 5 vertices. Okay, there's a path. Okay, so suppose that's your source. This is then a shortest path. There might be shorter paths, so let's throw in a few more edges. But maybe these are costly edges, so maybe this is the shortest path. You see what I'm saying? It all depends on the weights. But the point is that this vertex lies at the end of a shortest path with, at most, 4 edges in it. So if I relax all edges 4 times, I will have first time relax this guy, second time relax this guy, third time relax this guy, fourth time relax this guy, assuming that this is the shortest path. If this to this to this was the shortest path, then the first time I would have relaxed that edge, then the second that edge, and the second pass that edge. So I make all these passes over the edge sets, and I make sure that every shortest path then is a subsequence of that relaxation sequence. Okay, but that's only true if Bellman-Ford if there are no negative weight cycles reachable from the source. What if there are negative weight cycles reachable from the source? Then what that means is some d value can still be improved. Furthermore, if some d value can still be improved, that is lowered, there must be a negative weight cycle reachable from the source, because if there wasn't one, all the d values would have converged by now. So what I've got to do is one more pass over the edge set and ask myself, could a relaxation improve the situation? And if it can, I've detected a negative weight cycle reachable from the source. So for each edge, ask if a relaxation would improve the distance to y. If so, return false. This short circuits the loop and gets you out of the algorithm. If you get through this loop without ever returning false, return true. So a true return value from Bellman-Ford says there is no negative weight cycle reachable from the source. In other words, it's true that we have solved SSSP. False means we have not solved SSSP because there is a negative weight cycle reachable from the source. Go ahead. Because there's no need to do that, because that new d value would be meaningless. We would not have discovered another path. We would have discovered a walk, because we would have gone twice around this negative weight cycle. Sure, that's detecting negative weight cycles or detecting cycles at all is good information, but it doesn't solve this problem for us. Yeah, I mean, the point of the algorithm is to solve SSSP by finding a minimum weight walk, right? If it's solvable, if there's no negative weight cycle reachable from the source, that minimum weight walk is a minimum weight path, and SSSP has been solved. All right, I hope that makes Bellman-Ford clear. It all rests on the correctness of the path relaxation property. Okay. Let n be number of vertices, m be number of edges. Initialization is theta n. Cost of relaxation is constant. Each edge is relaxed n minus 1 times. So loop 2 through 4 costs theta m times n minus 1, right? M times the number of edges times number of times that loop executes, n minus 1. But that's theta mn. So the total cost is this plus this, and this is at least as big as that. I'm sorry, this is at least as big as that. So loop 5 through 7, that just goes over all edges. That's cost is theta m. If I add this and this and this, the highest order term is theta m times n. Considerably more costly than, say, BFS, which was theta m plus n. Okay. Well, that's the price we pay for having weights. Now, it turns out we can do much better than theta mn if we eliminate the possibility of negative weight edges. And that's what Dijkstra is all about. So this is chapter 24, 24.3. Seven, this is 8. Okay, so, well, I think I'll just skip that page. I'll just give you this. It's written so neatly here, and it'll save time. So the 7, this is page 8. There's Dijkstra's algorithm. Again, first initialize. Now, whereas Bellman-Ford relaxes all edges many times, n-1 times, a huge number of times, Dijkstra will relax edges at most once. Each edge is relaxed at most once. That's nice. So it's a lot more efficient. It uses a set S yeah, I should have left this, sorry. Here, I have to say something. A few words about Dijkstra before I show it to you. Requires weight of each edge be non-negative, right? No negative weight edges. It maintains a set S of vertices whose shortest path weights have been determined, whose minimum path weights have been found. I guess this is a bulleted list. Next bulleted item. It also maintains a min priority queue which I'll refer to as Q. Q is always of vertices. So what's in the min priority queue, the records in the min priority queue are in fact vertices. And as a set, Q is always equal to the whole vertex set minus S. It's everything, all vertices that whose D values have not yet converged, or at least not known to converge yet. I haven't told you what the structure of this min priority queue is until I tell you what the keys are. The keys in this min priority queue are, wait for it, D values. So the distance estimate for a vertex, that's the critical value attached to that vertex, considered as a record. Those are the D values. Those are the keys. Okay, so here's Dijkstra. Initialize G with respect to S. Set Okay, that's a little s, that's a capital S. Sorry about that. Initialize capital S to be the empty set. Initially, we haven't found any no d values that we know of have converged. Set the priority Q to be the entire vertex set. Keys are d values. So in other words, if we're implementing this as a min heap, then we have to, this is a call to build heap. Or if you like, a call to the priority queue constructor. Right? That's what build heap is, the priority queue constructor. Now, while Q is not empty, starting to look a lot like BFS, isn't it? Well, the queue is not empty. Extract min. So take the smallest d value, or take the vertex with the smallest d value and extract it from Q, the priority queue. Add it to S. So automatically S and Q are maintained as opposites, as complementary sets. And then, for all y adjacent to x, relax the edge xy. So relax all edges emanating from x, all edges having x as origin. And that's all. You keep doing that until you've extracted everything from the Q. Notice that the first thing, on the first iteration of this while loop, the first vertex to be extracted would necessarily be the source. Because what are the d values after just an initialization? The d values, that's the keys, are 0 for the source, and that's the best, so that's at the root. Remember, it's a min priority queue, so smallest at the root. And all the other nodes in the tree are infinite. Thinking here in a heap implemented priority queue. Okay. Now, something I want to tell you about relax that we have to keep in mind. Relax changes a d value. So that changes the d value of y, doesn't it? Potentially changes the d value of y. And that's changing a key in the priority queue. And you can't just reach into a priority queue and change a key. You've got to keep the priority queue structure intact. And that implies a call to decrease key. Remember, a max priority queue has a method called increase key. A min priority queue has a function called decrease key. So implicitly, relax contains a call to decrease key. So we'd need to rewrite relax explicitly so that it contains this priority queue operation in it. If dy is greater than dx plus weight of xy, call decrease key on y to that new d value, that smaller d value. See how it doesn't really matter if we considered that equality or greater than to be an error condition or not. And then set parent of y to be x. I will figure out the runtime and do some examples next time, I guess, because I'm now out of time. And I'm now not worrying about time anymore. I've given up. Can't worry about time anymore. Anyway, I'll see you Friday. That'll be our last day. We'll wrap up. I don't know what we'll do, but we'll do something. Turn in your homework if you didn't already.
Are you walking out to your office?
I am.
Mind if I tag along?
You may.
Cool. I was gonna